Good day all, myself Bipin Wilson, PhD student here at IIT Bombay, Mumbai, India. This is our work on a low-cost autonomous surface vehicle for shallow water bathymetry surveys. Bathymetry is the measurement of depth of water bodies such as ocean, sea or lake or even riverbed. Accurate and cost-effective mapping of water bodies has an enormous significance for environmental understanding and navigation. However, the quality and quantity of information we acquire from such environmental features is limited by various factors including cost, time, security, and the capabilities of existing data collection techniques. Measurement of water depth is an important part of such mapping, particularly in shallow locations that could provide navigational risk or have important ecological functions. Erosion and deposition at these locations can cause rapid changes that require repeated measurements. In this work, we describe a low-cost, resilient, unmanned autonomous surface vehicle for bathymetry data collection using side-scan sonar. We discuss the adaptation of equipment and sensors for the navigation control and data collection for the bathymetry data, and also give an overview of the vehicle setup. This autonomous vehicle has been used to collect bathymetry from the Pavai Lake in Mumbai, India. So we used a catamaran kind of structure for our autonomous surface vehicle. Catamaran structures have higher stability due to the wider beam, lesser power requirements due to smaller hydrodynamic resistance, and shallower throat, which helps in shallower areas. Since the acoustic and ultrasonic signal generated by the sonar transducer should be perfectly coupled with the water, and the sensor should also be shielded from the effects of turbulence, design of the components, propellant, and sensor placement was planned accordingly as shown in figure. To ease the implementation, we selected a readily available catamaran hull and 3D printed the required structure on them to safely incorporate the electronics components. So these were the main electronics components we used. So sonar we choose Hummingbird Chirp side imaging GPS G2, and controller was Pixox PX4, and positioning system was GNSS U-Blocks Neo MI10, and we used differential mode of control for the driving our vehicle, and for that we used two brushless motors with the electronic speed controller ESC, and we used two power supplies, one for the sonar and another for driving our vehicle. So to drive our vehicle, we have two 8000 milliampere lithium polymer batteries. We used 18650 lithium ion batteries to power our sonar. And to have a margin of safety, we also connected a RC transmitter receiver to our vehicle to take a control if something unexpected happens. And we have done the calibration in our controlled environment in the IIT Bombay swimming pool. So using that, we done the calibration for the depth and for the controller. The study area was Pavai Lake, located in Mumbai, India, which is an artificial freshwater lake, spreads over around 2 square kilometers with the corresponding geocoordinates as shown here. And the data acquisition was done during summertime of month of March, and during that time, because of the water weeds, we could cover the entire lake. As we can see from this satellite images, the shores were full of water weeds, so we couldn't cover those areas, and this image shows the corresponding flight path planned for this survey. We obtained the results. The data files were interpreted using a software, called Reef Master. Final map is obtained as shown in figure after interpolating the data points using triangular irregular network. Following findings were obtained from the we had obtained a total volume of lake as around 4 million meter cube, and total mapped area of around 1.7 lakh square meter, and average depth measured was around 2.1 meter, and maximum depth obtained was 5.83 meter. The results of the survey shows that the technique is suitable for monitoring in shallow areas. The independent system can remain on duty as long as we have enough energy, and the autonomous system can adjust on-site environmental changes itself or to survey tasks with advanced mission planning or decision-making capabilities on board. The modest size of the model decreases the likelihood of wind catches since the top half is aerodynamic and has little surface presence. The stability and shape of the streamline also assist the model to cope with the difficult environmental fluctuations and also enhance autonomous surface vehicle management. It should also be noted that although the system can collect data independently, there is a requirement for considerable amount of human labor and resources to manage and implement such systems. New sensors and techniques can be integrated into the system to improve vehicle independence, and efficiency.